Music. A unified theory of everything has a monumental task on its hands. It must bring together the strangest elements of quantum mechanics and relativity, the rules on the macro scale and the micro, which is really hard to do because there are some very weird things going on in the quantum world. Uncertainty quanta superpositions. So let's begin there. After my last video on this topic, I got loads of different comments from you all eager to hear my take on the answer to everything. I claimed last time that I believe some form of string theory offered the best chance at a unified theory of everything. It's time to show you how much heavy lifting strings can do on the quantum scale. I'm Alex McCone, and you're watching a Stram. While I don't claim to have solved the theory's mathematics, I believe that I've come up with a model that pieces all the phenomena together. Quantum physics' mathematics has rapidly overtaken its understanding of why the things we observe are going on. Let's try to help conceptual understanding catch up. As I said in my last video, it all starts with strings. Let's discuss a few properties of a vibrating string. This will help us to see why they lend themselves to quantum principles. We need to start with that first word, quantum. Simply put, quantum is derived from the same root as the word quantity. It's the strange principle that on a small enough scale, the universe seems to work in discrete quantities rather than operating on one continuous scale. This is a little unintuitive, much like many things in quantum mechanics. So let's illustrate what we mean with an example. If you are running, I could ask you to half the speed you're running at. You could half your speed again and again and again. Is there a limit to how many times you can half that speed? While you might struggle with the precision necessary to do it in classical physics, there's no reason you couldn't keep halving and halving your speed indefinitely, as there's no limit to the number of times you can divide a number by 2. There's always a smaller number. In the quantum world, this is not so. When it comes to energy levels, momentum, and other attributes, when you reach a small enough number, you discover that the universe does not work on a continuous scale, but rather in discrete quantities. An electron in a hydrogen atom can have exactly 3.6 electron volts of energy, or it can have 3.4 electron volts. But under no circumstance can it have an energy level between those values. This has been proven experimentally. A theory of everything must make use of an underlying universe geometry that is fundamentally quantized. The concept of some kind of web of strings fits that bill well, particularly when you bring in the transverse standing waves and harmonics. When plucking a guitar string, a standing wave can form that has one peak or two, but not a value in between those. This is because harmonics are formed by a combination of waves traveling along the string in one direction, perfectly resonating with waves traveling in the other. If the speed or frequency of the waves don't line up perfectly, the two waves will ultimately disrupt each other, leading to the collapse of the standing wave. Only waves with just the right amount of speed and energy can create standing waves on a given string. So immediately, we have an interesting mirror to our observation that subatomic particles have quantized momenta and energy levels. So do standing waves on strings. The next interesting point to note about waves is that by combining the correct sequence of sine waves, you can create any wave pattern of wave you might desire. Handy for creating the rich complexity of a universe. This mathematical principle was first discovered by Jean-Baptiste Joseph Fourier, a French mathematician, and is very useful in the study of heat transfer and vibrations, as it works the other way too. Any wave can be broken down into a number of constituent sine waves. When two waves try to occupy the same place, they will amplify each other if they're both rising or both falling, but will cancel each other out if they're in opposition. This can lead to all sorts of waves being formed. Square waves, intermittent waves, and even waves that only have a single peak and are flat at all other locations. This becomes easier to do the more waves you have to overlap. This is an interesting observation as it helps answer an important question that any theory of everything must be able to answer. Where do particles come from? When I say particles, I'm not specifically talking about molecules or atoms, but the components that make these objects up. Atoms split into protons, neutrons, and electrons. Protons and neutrons split into quarks, and there are leptons and bosons. Without needing to go into exactly what all of these things are or why they have some of the weird names that they do, I mean, who decided to call a quark strange, charm, or bottom? It's enough to say that they come in many different flavors. These are the smallest building blocks of reality that we know of so far. Why do they exist? Well, in a model using strings, they are the rising and falling of a wave. This matches Einstein's observation that mass and energy were essentially just the same thing in different forms, as laid out in his E-series MC2 equation. A wave is the motion of energy. Mass can be that too. The narrower the peak of the wave, the more defined a particle is in terms of its location on that string. You might take issue with the idea that both of these waves represent the location of a single particle. However, curiously, this matches another important facet of particles. They sometimes are a little vague about where exactly they are in space. If you know much about quantum mechanics, you have likely heard of Heisenberg's uncertainty principle. This is the idea that we cannot know a particle's momentum and position at the same time. We get a decent approximation at large scales. It's pretty easy to see where you are and where you're going, but at small enough levels, this becomes impossible to do. The more precisely we know where a photon is, the less information we have about its momentum and vice versa. This isn't just because we have bad techniques for observing them. This is apparently a fundamental truth. If we think about particles being the sum of many overlapping waves, however, this suddenly makes a lot more sense. Take a look at this wave. It is perfectly defined in terms of where it is going. But if we consider the peaks of this wave to represent the location of the subatomic particle, or at least the possibility that the particle is at this location, there are a lot of places it can be. So for this given string, we have perfect knowledge as to its speed and direction, but are uncertain about its position in a given space of string, perfectly in line with Heisenberg's uncertainty principle. If we converge several different waves into a single point, we can take advantage of Fourier's mathematical trick to cancel out some of the peaks of our wave. The more waves we add coming in from different directions, the more our particle becomes defined in space. But look at our particle now. How many strings are running through it? Each of these is a separate vector line representing momentum in a different direction. It's no longer quite so possible to pin down where this particle is going next, as there are several options that could be true. Perfectly pinning down a particle in terms of its location would require vector lines that could lead anywhere. This is starting to get into territory where you would need information from the entire universe before a single particle can be truly solved in terms of its location in space and time, which is a little headache-inducing. Perhaps the universe makes do with close approximations most of the time until someone looks closely. For this model, we must discard our concept of a particle as a localized object, but instead, we define them as the convergence of different waves coming together at a single point and then diverging again. This divergence doesn't feel right to us. We are uncomfortable with the idea of our particles only being really there at a given moment and dissipating afterwards. However, those of you familiar with the double-slit experiment, which I have covered in an earlier video, recognize that this is an uncanny match to another odd experimental result. A single photon released from an emitter and passing through two slits will somehow pass through both slits, interfering with itself on its journey. The photon reaches the far detector as a single particle, again indicating a new convergence at that point. But by sending many photons along this path, it becomes clear that interference is taking place in the intervening space. The photon seems to leave as a particle and arrive as a particle. But in the intervening space, it takes on the properties of a propagating rippling wave. Already we begin to see how some of the strangest aspects of the quantum world fit with the idea of strings carrying waves of energy. But this is only the first part of my model. To really see how much a theory matches the universe around us, we need to explore the motion of particles across time and space, to better understand entanglement and superpositions. And to do that, we need to explore how strings lead to gravity, time dilation, and other principles of relativity on larger scales. We need to have a clear concept of how time works. My model accommodates that, but it will have to wait until my third video in this series to fully explain. In the meantime, do you agree with what I've said so far? Are there other aspects of quantum mechanics that you feel suit or do not suit the concept of strings? Leave a comment in the description below to let me know. You've been hacked. Those 3 words can be the ultimate gut punch. When you read them, any feelings of safety and security get ripped away. Whether it's your personal messages, your social media passwords, your bank details, your company files, or anything. The consequences of having messages that were once private become public is an awful feeling with potentially dire consequences. So it's no wonder that truly unhackable encryption is such a sought-after technology. And China may be leading the way to just that. How? It's all thanks to a tiny Chinese satellite, a record-setting experiment, and a tantalizing new technology. One relying on that magic word, quantum. And according to scientists, the method China used, quantum key distribution, promises to be unhackable due to fundamental principles of quantum physics itself. But what is actually going on beneath all the hype? Are we really at the dawn of an impenetrable secrecy forever? Or will that enigmatic word quantum be the death of secrets instead? Music. I'm Alex McCone and you're watching Astrum. Join me today as we dispel the murk and the mystery around the new era of quantum satellites and communication, and reveal exactly how quantum encryption could change our world forever. Tricks to keep our messages secret have been around for thousands of years, almost as long as humans have had written secrets. For example, Julius Caesar used a cipher in his messages to appear like unintelligible nonsense to an enemy, but they could be easily decoded by his generals or friends who knew the trick. The idea Caesar used was simple. For every letter of the alphabet, he simply replaced the letter with another letter a set number of places further up or down the alphabet. For example, if he moved everything right 3 spaces, then A would become D, B would become E, and so on. X would wrap around the alphabet to become A. In this way, Caesar could keep vital information secret, garbling phrases like this one. But as long as you knew the number of places he moved the letters along, in this case 3 to the right, then you could easily move everything back to reveal the true and important message. Astrum is great. In this case, that single piece of information 3 to the right is the key that allows you to unlock the cipher. And encryption has been making use of this same essential concept ever since, albeit with a little more complexity. Unfortunately, this cipher has an obvious weakness. There are not that many letters in the alphabet, only 26. So, if you came across a message encrypted with Caesar's cipher, you could try moving everything along once, then twice, and so on, until the words started making sense. At most, you'd only need to try moving letters 25 times, and you could crack Caesar's code. It would only take a few minutes to know if you were on the right track. This method of encryption hacking is known as a brute force attack, making guesses at the key again and again until the encryption lies decoded at your feet. It is a valid strategy, provided there aren't too many options of what the key could be. Of course, encryption experts over the years worked out more and more complicated ways of jumbling up the letters to make it harder and harder to crack through brute force. For instance, why keep all the letters of the alphabet in order? Keyword ciphers don't worry about that. This second type of cipher works by simply deciding on a keyword and then laying the rest of the alphabet in their normal order after that keyword. Using the resulting jumble as the starting point of your cipher means that a code cracker will never be able to break your code by simply moving everything along. Now, they need to know the keyword, or do they? Technically, with sufficient patience, this type of encryption is still crackable even without the key. Of course, there are approximately 43 septillion ways you could rearrange the alphabet, which naturally would take far too long to try each option individually. If you tried one arrangement, it would take longer than the history of the universe. But it is still technically crackable through brute force. If you find a way of speeding this guessing process up, it would take humans far too long to do something like this. But once the computer was invented in the early 19th century, encryptions that were not robust enough could fall to computers making guesses much, much faster. If a human guessing is like a hammer hitting the door, computers are like jackhammers. Modern CPUs can perform billions to trillions of calculations per second. While it would still take a computer a long time to crack a keyword cipher, trillions are far less than septillions. After all, this time can be consistently reduced by bringing more computing power to bear. There is a fear that government agencies like the CIA have secret supercomputers with endless CPU brute forcing their way through the encryption of messages. To combat this, modern encryption does not specifically rely on ciphers anymore. Instead, many types of encryption, such as the widely used RSA crypto systems, rely on complex mathematical problems for which there is no known algorithm a computer can use to solve them. RSA works by taking two massive prime numbers and multiplying them together. The resulting number, called the modulus, is part of the public key that is shared with others. To unlock the encryption, a hacker needs to know which two prime numbers were used to create the modulus. And there's no easy way to factor it back into its prime numbers. Even a supercompute would struggle. Ultimately, the principle behind encryption has increased in complexity, but mostly works under the same basic idea. Messages are muddled by mixing them up according to some kind of rule. And if you possess a certain key, the message can be unscrambled. Technically, those messages can be unscrambled through brute force methods even without the key. But the keys have become so complex that even with powerful supercomputers, brute force methods supposedly would take thousands of years to be effective. So our messages are safe then? No. Because there is a point of vulnerability. If you want to decode an encrypted message, the sender of the message still needs to give you the key. If this key can be intercepted, the encryption can be undone without any need for brute force methods. And so we turn to quantum encryption, and what China just achieved with the Mosey satellite. For 4 decades, scientists have theorized about a method of sending encryption keys that is completely irrefutably unhackable. Very cleverly, they don't rely on simply being too complicated for hackers to bother, but rather utilize the fundamental principles of the universe. The principles of quantum superposition and uncertainty. We know that particles, although they appear solid and immutable up here in the regular world, behave very strangely on a small enough level. Specifically, they behave like particles and waves at the same time. Now, you can measure the position of a particle, but you'd struggle to determine its momentum. On the other hand, a wave's momentum is easy enough to measure, but you'd have to settle for measuring its wavelength rather than its exact position. The result of this is that we cannot actually know both the speed and position of particles at a quantum level at the same time, at least not with a good deal of uncertainty. This is known as Heisenberg's uncertainty principle and is a proven fact of quantum physics. Weirdly enough, we also know that once the particles are observed, they settle on one of the two states. It has been proved through experiments like the double-slit experiment that a single particle can travel through multiple paths at the same time and only settles on one path or the other once it is interacted with. Until then, it travels down both paths in what is known as superposition, left and right. Like Schrödinger's famous cat, neither alive nor dead until the box is opened and it is seen. These principles of quantum physics make it so that once a particle is observed, it behaves differently from when it is not observed. And in the early 1980s, scientists realized that you could incorporate this into a very safe way to send encryption keys. If you converted your encryption key into something physical, a stream of photons for example, and came up with a clever enough method, it would be possible through statistics to see whether your photons had been observed or not between the sender and the receiver of the key. In other words, it would be possible to see whether some sneaky hacker had intercepted your encryption key in transit, noted it down, and then sent it back on its way to its original recipient, hoping to remain undetected. According to the principles of quantum superposition, the moment such an observation occurred, the key would subtly alter, and this alteration could be detectable with the right know-how. And knowledge is power. If you know whether your encryption key is observed or not, you can hold off on sending the private message until you have confirmed you have an unobserved key. The message itself can then be safely transmitted through the regular channels. This is brilliant. Of course, getting particles to travel long distances in a state of superposition is not actually very easy. If they bump into an atom along the way, it could collapse the superposition. But scientists realized that this problem could be minimized if most of the journey was done in a perfect vacuum, or in other words, if the particles could be transmitted through space. And it is China that first brought this theory into reality. Just 1 month ago, at the time of writing, on the 19th of March 2025, Chinese scientists announced that they had broken a record for using a satellite to distribute a quantum key between Beijing and a South African university near Cape Town. To do it, they used a tiny microsatellite called MOSI, which sent pairs of entangled particles across the massive 12,900 kilometer distance. Each individual entangled pair had a risk of collapsing en route. But with enough pairs, recipients on each end could compare parts of their code and statistically verify that they're particles, and thus the key they were carrying were either observed or unobserved. MOSI is only 23 kilo, an order of magnitude smaller than previous attempts at a quantum satellite. And the successful completion of its mission opens the way for an entire distributed network of interconnected quantum satellites, transferring quantum keys across the globe so that people can send messages in safety. Imagine a world where every financial transaction, every email, and the entire internet was completely unhackable, where true privacy was a guaranteed fact of life thanks to watertight encryption. For those who value such privacy, it will be a utopia. Or will it be? Is it all a little too good to be true? There is one facet of this that gives me pause that nobody seems to be addressing. Quantum key distribution works via satellites distributing quantum keys, which are completely unhackable. All well and good, but note what I'm saying there. They distribute the keys, not the messages themselves. In my research on this subject, I have repeatedly seen the assertion that the encrypted messages can be safely sent via the normal channels because you are able to confirm via quantum key distribution that no one has intercepted your key. The reason they do this is because quantum technology is not yet very good at sending large amounts of data. A key is fine, but a larger file is better sent through conventional means. This is very clever and seems logically very sound. But how is this any safer from brute force methods than current encryption? Brute force methods work by guessing keys one after another after another. They do not work by intercepting keys. Certainly there are hacking methods that do work by trying to intercept the key, as this is far easier than the vast computational power required by brute force. But if you do have access to a powerful enough computer, I've not found an explanation for why you care if the key is quantum or not. Either way, it's the encryption itself that is the defense, not how well you've hidden the key. I also imagine a world where hackers don't care if they're noticed or not. While this would mean that the secret message was never sent because a safe key was never found. If hackers just kept their eye on a satellite, it would effectively deny the use of that satellite to its owner. Denial of service attacks are a nefarious method hackers use to bully people into giving them what they want. Imagine if your vastly expensive quantum satellite could be rendered a useless hunk of metal because too many messages were getting intercepted. But back to the first concern. Certainly, you might point out that most people do not have access to powerful supercomputers. So for the average hacker, brute force methods are simply not an option. But a new technology is coming that could change all that. And it is also using that magic word, quantum. Experts believe that the first publicly available quantum computer is just a decade or so away. Quantum computers likely won't replace all classical computers. They're a bit niche, and some general everyday tasks like browsing the web are actually just as fast on a classical computer as a quantum one. But thanks to a quantum computer's ability to compute using CQITs that can be in a variety of superpositions at once, rather than just bits that can either be 1 or 0, there are certain specific tasks quantum computers are much faster at, scarily fast, unnervingly fast. And one of the tasks it's thought they'll be much better at is brute forcing encryption. This is not a hypothetical technology. Quantum computers are already here in the hands of powerful corporations and governments. In 2015, Google claimed that its D-Wave computer had proven itself 100 million times faster at performing certain tasks than a regular desktop computer. For reference, it supposedly did in a second what a regular computer would take 10,000 years to do. Think of the implications of that. Modern encryption is only safe from brute force methods, because encryption is so complex nowadays that it would take a computer thousands of years to work through all the possibilities for keys. But what happens when quantum supercomputers get into the hands of every hacker out there? When those encryption methods praised for being safe, because they would take thousands of years to hack, are crackable in moments. Suddenly, no regular encryption is safe anymore. This is not just me being alarmist. The US government fears this too. The International Institute of Standards and Technology, an agency within the U.S. Department of Commerce, is so concerned about the arrival of this technology that they are telling companies to start preparing for it now by changing the fundamental nature of their encryptions. After all, although quantum computers are not here yet, there's nothing to stop hackers from collecting encrypted messages and financial data now and then, just holding on to them until the day arrives that they can get their new quantum computer from the shops. Passwords, financial transactions, and certain sensitive messages will still be sometimes relevant a decade from now. And once those messages are all cracked with ease, a wave of crimes and exposed secrets will sweep across the world. But there is hope. The NIST has been compiling a defense against the threat posed by quantum computing, and this defense does not lie in unhackable quantum keys, but something more mundane: algorithms. Yes, similar in idea to the algorithms that are protecting encryption already. However, rather than protecting messages by scrambling them with complex mathematical problems that will take a long time to solve, the NIST is preparing 5 algorithms that don't care how much computational power you have. For instance, their EFIPS 204 standard makes use of mathematical lattices, points in space with an arbitrary number of dimensions to work in. The key requires you to find a particular pattern within the lattice, like locating the specific path in a 5D maze. As there is no known mathematical algorithm that can find this path efficiently, there's no algorithm that you can give to a quantum computer. They struggle with the extra dimensions and can't solve the problem any faster than a classical computer. To put it simply, it doesn't matter how strong your muscles are if you don't know where to hammer. EFIPS 204 is an example of a quantum-resistant or post-quantum algorithm. And we're back to where we started. A new technology has emerged, and both hackers and encryption experts are handed the same new toys. Each made massive advances in their field. But as with the rise of computers, the situation stabilizes. Computers threaten privacy, but then ultimately restored it. Quantum technology both improves privacy and finds new ways to threaten it. The cycle of history repeats itself, with developers creating new algorithms and hackers trying to find points of weakness, and each success on one side drives the other to try all the harder. So, have quantum satellites ushered in an era where privacy is guaranteed? I highly doubt it. Even if the key is completely secure, hackers can always find another way in. But equally, has quantum computing ripped down every defense and ended secrecy forever? I also find myself skeptical. Brute force might soon be more effective as a hacking tool, but already companies and governments are pivoting to new defenses that can weather the coming storm. But who can say for sure? Right now, the future is in a sort of superposition of its own, both secure and unsecured, private and public. And much like all things quantum, that superposition will only collapse once it is observed firsthand. On a day 35 years ago, a collection of atoms and particles combined into a discrete complex structure that somehow was more than the sum of its parts. The elements involved were mainly oxygen, 65% of the total mass to be exact. But the structure also included 18.5% carbon, 9.5% hydrogen, 3.5% nitrogen, and a touch of calcium and phosphorus. These elements combine in our universe all the time. But what was surprising about this particular structure is that it got up one day and identified itself with the name Alex McCone. It was me. The same thing happened to the elements that made up you and everyone that you know, and the elements that comprise everyone that has ever lived, which when you think about it, is decidedly odd. How does what is essentially a pile of rocks, air, water, and chemicals have a sense of identity? And yet somehow, that is what happened. Consciousness arose from dust, and seemingly keeps arising. Which begs the question, where exactly did consciousness come into this equation? At the end, with a fully developed human brain with an animal brain, a plant, a single bacteria, or can we make the claim that if matter can be conscious, a single atom of matter is conscious too? I'm Alex McCone and you're watching Astram. Join me down the rabbit hole today as we enter the wonderland that is consciousness, our best theories on how it arises, and as we attempt to answer one simple question. Can a particle be conscious? To begin with, I'll acknowledge that on the surface that seems like a facetious question. Most people have a fairly good gut instinct about what is conscious and what isn't. You are conscious. After all, you have a sense of identity. You make choices and you consider the information your senses bring you and you ascribe value to what you experience. To paraphrase a famous philosopher called René Descartes, we cannot doubt our own consciousness because otherwise who would be doing the doubting? We think therefore we are. Beyond that, we are usually quite confident of the consciousness of the fellow humans around us. Although we cannot see inside their heads, we can usually ascribe to them the same capacity for thought and experience that we enjoy. Except, of course, when they're on the other side of the political spectrum to us. But our instincts start to get a little more hesitant after that. Researchers into animal behavior were asked in a survey whether they believed the animals they were studying were conscious. While 92% of the respondents were happy to say non-human primates were conscious, only 73% extended this attribute to other mammals. For octopuses, it dropped to 64%, birds 61%, and for insects, only 51% of the sampled researchers believed them to have an intrinsic sense of self. It's likely that the general population feel a similar way. However, here we have already strayed into the big problem of consciousness, belief, and feelings. The above survey was based on the gut instinct of those surveyed, as conscious experience is very difficult to prove. Just consider the debate surrounding whether artificial intelligence counts as consciousness when it can mimic humans quite convincingly. Is a recorded message conscious? A written note? All this is hardly a solid foundation for good science. We need something a little more precise and measurable if we are to answer whether matter itself can possess consciousness, which is unfortunate as no such test currently exists. In fact, there is very little consensus among philosophers and cognitive scientists as to what consciousness or qualia instances of subjective conscious experience, as they call it, actually even is. There are plenty of theories as to how we get it. Global neural workspace theory notes that particular parts of the brain light up when we think about certain things. It attaches consciousness to these areas, the parts of the brain doing front-of-the-brain thinking. It points out that we can only perceive one thing at a time in the stage of our mind. For instance, have you seen the optical illusion of the vase in the face?